All right, so let me share my screen and oops, wrong one. Share. So I want to share solutions. All right, so you should now see basically the Newton's method code, and it should say demo student Newton's method code at the top. Is that what you're seeing?
Yes, the
Okay.
student, yes.
All right. So what you want to do if you're using, whether you're using CoCalc or whether you're using Google Colab, you want to upload the file into the system so that you can start executing and changing data. All right. So are you using Google Colabs or are you using CoCalc?
I'm using Google Colabs.
All right. So do you have the file open?
Yes, so I can edit it and everything.
All right. Perfect. Well, let's get started. So what we're going to do is we're going to execute all of the examples and then we're going to copy and paste lines of code and change things as we need to. So starting at the top, this first line is just text. So that's nothing to execute. But anytime you see these square brackets, that's something to execute. So you're going to want to go in here and change the name to your name. And then if you're working alone, you can write, I'm working alone, or if you're working in a group, you can write your group members' names, right? So the first thing you want to do is change that. And so I might change mine to one, right? And once you've changed it, then you want to hold down the shift key and hit enter at the same time. And you'll see that it's going to, put up some kind of symbol to indicate it's still running. And then when it's done, you'll see this little check mark off to the side and it will assign it a number. So in this case, it assigned it number 1. So you know it's executed, right? And it's going to print out your name and who you're working with. Now, the next command is going to, SymPy is symbolic Python. So those are the symbols. So Python, being a computer code, doesn't understand the difference between a number and a symbol. So it can either treat things as strictly numbers or it can treat them as symbols, but it can't do both at the same time. So NumPy will import things as numbers like 5, 10, whatever, and SymPy will treat X as a variable instead. So we need both NumPy and SymPy. So NumPy down here is numeric Python, and SymPy up here is symbolic. Colorama just lets us print out our solutions in different colors. And Matplot library is the math plotting library. So this is all the commands it takes to print out a plot. So we want to import that, but being kind of lazy, we don't want to have to type matplot live.pyplot every time. So we import it and nickname it PLT, right? So click anywhere inside that box and then do Shift Enter again, and it's going to calculate and do whatever. And then it should assign it a number. And you can see it assigned it the number 2. So you know it's executed, right? If there's no number, it's not executed. If it starts numbering over, it's gone to sleep and you need to go and tell it to run all the cells from above, all right? So if it ever goes to sleep and starts renumbering from 1, you will want to click on runtime and do run above or run before, right?
Okay.
It's still awake. So now we're going to look at the next part. This tells us we want to set our function. So we're looking at the square root of x plus 1 over x squared minus 3. So in here, the first thing we do is using SymPy or symbolic Python, we're going to set x to be a variable. And the name for that is symbols. And then we're going to define a function, but this will be a symbolic function because we just made x a variable. So it's not going to ever give us a number. It's always going to give us an expression, all right? So I named it f underscore sim for symbolic function, all right? Can't give me number values. It can only give me expressions. And then I'm going to type in square root parentheses x. So if I were doing a number and I really wanted the square root of the number, I would do np dot square root or something. And then plus x, and the power is 2 asterisks in a row to the -2 minus 3. So that's this function here. df dx symbolic is what I call the derivative of that function. So I call up the derivative with the diff command, and I tell it to take the derivative of the function fsim with respect to x, all right? So far I've made x a variable, set a symbolic function, taken the derivative of the symbolic function. I also need the function to return actual numbers so I can plot it, right? Because if it doesn't have numbers, it won't plot. So I'm going to use a command called lambdify. Lambdify is a way of defining a function quickly without having to go through the define, function, return, all of that. So we just put f equals, so f is going to give me numbers, fsim is symbolic. Lambdify, parentheses, then I tell it that I want x to be the variable and fsim to be the function, right? And then I also need the derivative to give me actual numbers. So I do df dx. So this is not symbolic. This is actual derivative values. And I do the same thing on df dx symbolic. So I have two functions that represent the same thing, but one of them will give me numbers and one of them only gives me the thing in symbols, right? And then I want to print out the function to make sure I got it in right. So I just click anywhere inside the box, hold down shift and press enter. And you should make sure that the function you get here matches the function that's up here. And it does. So I'm good, right? And I think it named it 3, right? So I can tell it's still awake, which is good. Because sometimes it does go to sleep and then you have to rerun the cells above it. They have to be run in order or it won't work. All right, so now I need to think about the domain of the function and I need to pick a bunch of x values so I can plot it. There's a command in the numeric Python, so np, called arrange that basically gives me a list of numbers. So for example, if I look at this command right here, x equal np dot arrange, I'm redefining x now to be a number, all right, not a symbol anymore, all right? So once I execute this command, x stops being a symbol and starts being a number. But I've already got the function and the derivative defined symbolically, so that's okay. This is going to start at 0.001 and go to 100 and divide it up by 0.1 and plot all those points. So it's plotting like, I don't know, 1,000 different points or what, I mean, a lot, okay? Now, why did I pick from 0.001 to 100? When I look at the function, I have square root of x. So x can't be negative. So I chopped off the negative end. But it could be 0. But 1 over x squared, x can't be 0. So I don't want to allow 0, but I want to get close to 0. So I chose 0.001. You could have done 0.0001, anything like that. If your function doesn't have a square root or cause 0 in the denominator, then you'd probably want to pick something like -100 to 100 or -1,000 to 1,000, not knowing, all right? And remember, the whole point of Newton's method is we're looking for x-intercepts, all right? Okay, so that defines x. And then I'm going to define y to be f of x. So remember, f was the numeric representation of my function, and y is going to be what comes out of the function. So these next commands are all to plot a graph. The first one gives it a title. The second one is going to label the x-axis and the y-axis, so I know what colors they are. And it's going to plot the function in a certain color. It's going to plot y values between -5 and 5. I'm only interested in where it crosses the x-axis. So -1 to 1 would work too. I just chose -5 to 5. I don't really care about seeing the whole function. I just want to know where it crosses the x-axis, right? Then I labeled the x-axis and labeled the y-axis. Plot legend is going to print out a little definition of what the graphs are. And then if I don't tell it to show the graph, it won't actually print out. So you have to tell it to print out. So all of this is good. So we're going to do shift and then enter. And it's going to execute. And you can tell it gave it number 4. So it's still awake. And you can tell that it looks like there's 2 x-intercepts here and here, right? But my scale goes up to 100. So I can't really tell what they are. So the next thing I want to do is get in closer. It's definitely before 20. So it looks like it might be 0 to 10, something like that. So all I'm going to do is re-execute the plot, but come in closer on the x-axis to where I think it has the x-intercepts. So what I changed was I added a command called plt xlimit. So it's only going to plot between 0 and 10. It can't plot 0 because it's undefined, but from 0 to 10, and the y values from -5 to 5. All the other commands are pretty much the same, although I did label it graph2. So shift enter, and it's going to label it 5. And now you can see right where the 2 x-intercepts are. So Newton's method works by finding a point close to the x-intercept, calculating the tangent line at that point, and seeing where it hits the x-axis. Then it takes that point, finds the value on the function, computes the tangent line there, and it keeps going until it finds something super, super close to the x-intercept, all right? So based on my picture, it looks like this one is probably, I don't know, it's less than 1, so you could call it, well, you could probably use 1. You could use 1, you could use a half, you could use 0.75, whatever you want to use. Up here, this one looks like it's about 9. So those are what we call the seeds. You have to tell Newton's method where to start, because if you don't tell it where to start, you could end up looking a really long time or forever. So the first thing we're going to do is we're going to set the seed to be 0.5, so close to the one on the left. We want to set the error. The error is how far the y value is away from the x-axis. So again, we're trying to find the point where the y value is actually 0, all right? So this says as long as it's within tens, hundreds, thousands to the 100,000th to 0, then it will say this is a good approximation, all right? But I can set how far off I want to be. So if I want to be closer than 1/100,000th, I can be. Now, max iterations, you have to put in a fail-safe because there are a couple occasions where Newton's method might go forever. There's a weird error that we'll see later when we do type 3, where it bounces back and forth between the same 2 numbers and never gets closer to the x-intercept. A computer doesn't know when to give up. So if you don't tell it to only run a certain number of times, it will look forever. It will burn up your machine. You'll have to unplug it to get it to stop. I mean, it can really crash your system. So maximum iterations is like a fail-safe. So I want it to do this tangent line calculation 30 times and stop. Or I want it to go until the y value is within 1/100,000th of 0. So between -1/100,000 to 1/100,000. So this just sets the seed, how far away from 0 I want to be, and how many times I want it to run. So I want to execute, shift enter. It doesn't have any output, but it will do that. Now the next long input line of code, this is defining the Newton's method program. So up here, you can see it defines Newton's method, and you're going to call it on a function. Oops, it keeps popping up for me. You're going to call it on a function called Newt. You're going to have to feed it the derivative. You're going to have to tell it where to start. That's x naught is the seed. And the error is how far away from 0. In our case, 1/100,000. And then what it does is it goes through and it says, okay, first let's evaluate the function at the seed. So it's going to evaluate it at 1/2. It's going to start counting at 0. And then it's going to say, as long as the absolute value of the function is greater than our error, right? So as long as the y value is more than 1/100,000, then I want to, and the maximum number of iterations is less than 30, then it's going to print out what the approximate value is, in our case, the original seed, the number of iterations so far, and then it's going to reset, all right? So what we're going to do is we're going to reset the seed to be x naught minus the f value divided by the derivative at that point. So we're basically using the tangent line. If we divide by 0 by accident, it'll give us an error message, right? And so when we're done, it's going to add 1 to the count, the iteration, and then it will repeat, all right? So if the absolute value of the function is greater than the error, then it will give us a negative error. So you either find a solution, this goes and goes and goes, and then if it goes 30 times and didn't get close enough, we set the iteration counter to be something that doesn't make sense. In this case, -1. Because it should go 30 times. If I get a -1, I know there's a problem, that it reached 30 and didn't find the answer, right? And then it's going to print out what it found. Now, all this line of code does is define the function Newton's method. It doesn't execute it until I call it, but it will define it, and I never need to copy this line of code again. So I need to execute it. So I'm going to shift enter, and that tells me it's 7. So it's still awake, which is good. Okay. So the next input line of code is the first line of code you're going to copy and paste into practice 1, part 2. All right. So you might go ahead and click in the box, and then on a regular computer, you would do Control A to select everything in the box, and then Control C to copy. If you're on a Mac, you would do Command A to select all, and then Command C to copy. So Control A, Control C, and then I click back in the box. Okay. This short line of code here is actually calling up the program, Newton's method. So I named it Newton. I tell it the function f, df dx. My seed was 1/2, and my error is 1/100,000. So I'm going to go ahead and shift enter and execute it. And you can see it's very, very fast. All right. So 0.5 is the seed I gave it, so it hadn't looked for it yet. Then it found the slope of the tangent line at 0.5 and found that x-intercept, which was 0.611, and it changed the number of iterations to 1. But the function f of 0.611 wasn't within 1/100,000th of 0, so it took this value on the function and refound the tangent line. And then it found the x-intercept on that tangent line, which was 0.6678. Changed the iteration count to 2. But the function at that was also not close enough to 0. So it found this point on the function, calculated the tangent line, found that x-intercept, which was 0.677. Still not close enough to 0 for the y value. So it computed the tangent line at this point, found its x-intercept, which was 0.7779600, blah, blah, blah. That one was within 1 over 100,000 of 0. So it stopped. So it called the function 9 times. The more often you call the function, the more work the computer does, so it heats it up. And in coding, we try to minimize the number of times we execute something. So it's not enough to just program it to run. You also want to program it to run with the minimum number of commands you can. Because the more commands, the more it heats up and the more it decreases efficiency, right? So you can see our y value is 7.89, blah, 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 times 10 to the negative 7. So basically we have decimal point 6 zeros, then 789,688, blah, blah, blah. So it is within 1 over 100,000, right? So my x-intercept is 0.677796, blah, 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 right? And the y value is practically 0, not exactly, but practically. So now we want to do it again on the second seed, 9, and we want to use more accuracy, all right? So this time, I'm going to set the seed to be 9, and I'm going to change the error to 1 times 10 to the negative 10. So decimal point, 9 zeros, and then a 1. That's pretty small. It's 1 over 10 billion, I think, it really close to 0. Then I'm going to call Newton's method again. I'm going to name it solution 2 because it's the second seed, and then I'm going to print it out, right? So I'm going to shift enter, and it doesn't have to run very many times. It runs 3 times, and it finds the second solution at 8.92483. That's where the original function, which looked like, where was it? This one. That's about where it crosses the x-axis. That's what the x-intercept is, right? So now what we want to do is we want to try practice 1. So the first thing we want to do is we want to click in the first box and then do Control plus V as in Victor or Command V, right? To copy all of that in there, right? Actually, I need to change the function first. So that one shouldn't go in there. So do Control Z as in zebra or Command Z to get that out of that line. Let's put this in the second line of code, all right? So the first thing we need to do is we need to redefine our function, all right? So we need to redefine the function, and then we'll call up Newton's method again, right? So the first thing we're going to do is we're going to find where we defined the function, and we're going to go copy that line of code and paste it again, right? So in this case, we are looking for, we have to return x to being a variable. Where'd it go? There it is. So right up here, above where it says graph the function, define suitable seeds. So I'm going to Control A or Command A, Control C or Command C. I'm going to copy all of that. I'm going to scroll down. And I'm going to paste it here. Right? So I want symbols, X to be a symbol. Now I have to redefine my F command, all right? So this time it's x squared times e to the x minus 1/2. For symbolic Python, we use exp parentheses x for the e to the x. So I'm going to come down here where it says square root of x and all of that. I'm going to highlight that and delete it. And then I'm going to put in x to the second power, which is a double asterisk. And then Python doesn't understand implied multiplication, so I have to make it explicit with a times symbol. And then I'm going to do exp parentheses x. All right, so that gives me x squared e to the x. I'm going to leave a space, minus space, and then you can do 1 divided by 2, or you could put in 0.5, whichever one you want. The other commands are not going to change. All right, they will redefine the derivative symbolically, redefine the numeric function, redefine the numeric derivative, and print it out. So now I'm going to do Shift Enter, and it should say x squared e to the x minus 0.5. Okay. Okay. Now, the next thing I want to do is find some graphs. All right, so I need to graph it. So I've kind of put this one in the wrong place. So I'm going to put my cursor on the bar in between those two lines of code, and I'm going to click code. It just adds an empty line, right? So now I want to find the first graphing command, which was right here. So I'm going to click in the box, and I'm going to do Control A or Command A, Control C or Command C. And then I'm going to scroll back down to practice one, and I'm going to put that in this box with Control V or Command V. But I have to think about the domain. When I had the previous function, I had a square root of x and 1 over x squared. So x had to be greater than 0. X squared, the domain is all reals. E to the x, the domain is all reals. Subtracting half just pulls the whole graph down a half, so that doesn't affect it. So I'm going to click in here where it says x equals np arrange, and I'm going to delete the first number and change it to negative 100 to 100 by 0.1s. I'm hoping that the x-intercepts are in that range, all right? The rest of it is fine. So that's the only thing I need to change in there. So then I'm going to click in here and Shift Enter. And I can tell that it definitely has at least 1, maybe 2 or 3 x-intercepts near 0. But I can't tell exactly where they are. So I'm going to insert another line of code. I'm going to scroll up to where the second graph command was, which was here. And I'm going to Control A, Control C, or Command A, Command C. And then where'd it go? There it is. Control V. And my X values. Okay, so before my domain was strictly greater than 0. So 0 to 10 made sense. But up here on the first graph, I think there's something over here on the negative side. So that doesn't make sense. So I might try maybe up here on my X limits, negative 10 to 10. All right, to see if I can see it all. That's the only thing I have to change. Then I'm going to Control Enter. And I can see it. It's not great. It's okay. I could try something else to see if I can get closer to it. I'm going to add another line of code. Control V, because it's still copied. I'm going to change the limit this time. Looking at this graph, it's definitely between -5 and 2. So I'm going to change this to -5 on the X limit to 2. And it's really close to the X-axis. So I want to spread it out vertically. So I'm going to change the Y limit from -5 to 5 to -1 to 1. So it's like zooming in on that part of the graph. Then I shift enter, and now I can see them more clearly. So it looks like there's one before -3, there's one between -2 and -1, and there's one between 0 and 1. I definitely have 3 x-intercepts, right? Does that make sense?
Yeah, so good. So far, so good. There.
So far, so good. Okay. All right. So next thing I want to do is I've identified the graphs, all right? We changed the domain. All right. Fourth copied line of code. Suitable seeds. For the seeds. So we have 3 different seeds. So the next thing we want to do, trying to make sure I'm keeping up with my graph over here, is we want to go to finding a seed. We need to set our error, our seed, call up the function, and print it out, right? So that would be error seed function printed out. So that would be this one right here. So I can click in the box where I set the seed to be 9 on the example, and I can Control A, Control C, or Command A, Command C, and scroll down. And this is going to be on part 2. So it's actually right here. Right? And I can go ahead and copy and paste it 3 times if I want to, because I have 3 seeds, right? Set the accuracy level to 1 times 10 to the -10. So those are all set correctly. Use the estimated values of the x-intercepts as seeds, all right? So we want to come and look at our graph. So I'm going to set maybe -3 to be 1, -1.5 to be 1, and 0.5 to be another, right? So down here, I'm going to set one of them to be -3 and one of them to be, what did I say, -1.5? And the other one looked close to 0.5, all right? So we might call this solution or solution 2. If you want to leave it solution 2, you can leave it as solution 2, or you could change it back to solution if you wanted to, right? So now what we want to do is we want to go ahead and execute it. So we're going to execute the first one. It iterates 5 times, and it tells me that the x-intercept is very close to -2.617, blah, blah, blah. The y value is -1.38 times 10 to the -15. So 14 zeros, then 138, blah, blah, blah. All right, so very close to 0. So this is a great approximation for the x-intercept. So that's one of them. Now I want to find the second one. So I click in this box, shift enter. I get about -1.48-ish, right? And that's also within my amount of error. It's better than what I was expecting. And then I'm going to execute the last one. And I get about 0.5398. And this time, the y value was actually 0. So I got it exactly, which is very unusual, right? Does that make sense?
Yes.
Okay. So that's it for the first part. Now we're going to look at some failures of Newton's method, why we had to set maximum iterations. So what we're going to do is we're going to start over again. There are 3 ways that Newton's method could fail. One is if the slope of the tangent line is 0. If the slope of the tangent line is 0, it's horizontal, so it doesn't have an x-intercept. So we don't have a way of setting a new seed to find the new tangent line. So that would cause it to fail. If that happens, the code will tell you, and you just choose a slightly different seed value. So if you pick 0.5, you might try 0.49 or 0.4 instead, and that will probably fix it. Type 2 is when you didn't give it a good seed and it just timed out before finding it. Type 3 is where it bounces back and forth between two values. The tangent line goes this way, then back to the first, then back to the second, on and on and on forever. So it never gets closer to the x-intercept. So we're going to reproduce type 2 and type 3. So the first thing we want to do is we're going to copy this line of code so we can Control A, Control C. This will be our first input line to put in the slot following practice 4, right? Okay, so the lazy idiotic way. So we're going to define a new function. This is the same commands we used up above, but we're defining a new function, x cubed minus 2x plus 2. So hold shift and press enter, and you can see it put out the function symbolically. And then we're going to be dumb, and we're not going to graph the function. We're just going to pick a seed at random. And we have no idea where it is, so we have no idea where the x-intercepts are. We just pick a number, right? In this case, we picked 50 with 1 times 10 to the negative 10, but I only made it iterate 10 times. So we're going to shift enter. We're going to execute. It goes 10 times. And the last time it did it, it approximated this with the y value of 0.9866. Well, that's pretty close to 1. That's not within 1 times 10 to the negative 10 of 0, all right? So it just timed out. So what it does is it tells me the number of iterations is a negative number, which doesn't make sense. So I know it timed out, right? So then we're just going to guess again and again and again and again. So first we're going to copy what we just had down here in practice 4. So this is going to go here below practice 4. So just leave it. You don't have to do anything to it. We're not quite ready for practice 4, but it's there. All right, so we're going to scroll back up to practice 2. We want to reset the seed to be 25, but we'll use the same error and 10 iterations. So I want to click in this box where I set the seed to be 50 and copy everything. Okay. So I'm going to come down here, and in fact, I might end up doing it more than once, but let's see. So we're going to set it now to be 25. So we're moving our seed, just trying to find it at random. We're going to execute, and it times out again. The last y value it found was 1.8. That is not close to 0. So it didn't work.
I pasted the wrong thing. Is there a way to like go back?
Okay, so if you paste the wrong thing, do a control plus the letter V as in Victor, right? Or no, Z. Z as in zebra.
Okay, cool.
And it will undo it.
Nice.
Right? Control or Command Z is the undo. Right? So get your error and your seed and execute. Now the directions say, if it works, go to the next section, but it didn't work because it timed out again. We're going to reset the seed to be 15, and we're going to run it again. So we're going to control paste, and we're going to change the seed to 15. And we're going to run it again. And this time I got 1.999. I mean, it's a y value of 2. That's not close to 0, so it didn't work. So I'm going to run it one more time at 5. Right? This time the y value is negative 526. I am not getting closer, right? I'm trying to find where it crosses the x-axis, so the y value should be 0. The problem is I didn't graph the function. If you don't graph the function, you don't know what's a good seed, right? You have to give it something close to an x-intercept to get it to find it, right? So we're going to stop working the idiotic way, and we're going to graph the function. Now, our function up here, I can find the function. was x cubed minus 2x plus 2. So the domain is all real numbers. So negative 100 to 100 is a good start. It is a cubic, so we kind of know what it should look like. So now I'm going to come down here and I'm going to graph it. I'm going to make sure that my domain matches the function. So negative 100 to 100. And this is just going to plot it out. So I'm going to shift enter. And I can see the cubic behavior, and there's definitely one x-intercept close to 0, right? So there's one close to there. So I want to get a little closer by restricting my x limits. So I chose negative 10 to 5, and I left it at negative 5 to 5, but you could change it to negative 1 to 1 if you want. And then shift enter. And now you can see it looks like it's really close to negative 2, all right? So we've got to estimate that it's close to negative 2. So now what I'm going to do is I'm going to paste in the seed definition again, but I'm going to tell it to use negative 2, all right? And I'm going to leave the number of iterations at 10 and the error at 1 times 10 to the negative 10. And then I'm going to execute. And it only took 5 iterations, and it got negative 5 times 10 to the negative 13th, so 12 zeros and then 5. So it's really close to 0. So my x-intercept is about negative 1.769. Right? So that's a type 2 error. You have to graph the function so that you can pick a good seed. Now let's look at type 3 error. So type 3 error is where it bounces back and forth between the same 2 values, and it gets stuck in an endless loop. This is why we set a maximum number of iterations, because otherwise it would never stop and it would hang up your computer. So we're going to be using the same function, the cubic, and we're going to set the seed to be 1. Now, you wouldn't know to set it to be 1. I know that that causes it to have this kind of error. So I set it up for you. So we're going to shift enter. And look at what's happening. The first root we gave it was 1. Then it used 0. Then it went back to 1. So it'll go back to 0, then back to 1, then back to 0, back to 1, back to... And the y values are never close enough to 0, so it would never stop looking, which is why maximum iterations is important. It will stop it, right? This is what's called a type 3 error, right? So the last y value it found was 1, which was too far away from 0 to be close enough as an approximation. So what we're going to do now is we're going to come down here, and we need to redefine our function. So this is practice 4. So this is the input line of code from way up above where we first started talking about the 3 types of errors, right? So you want to copy that off. So this is coming from failures of Newton's method, the first line below that, which is for us 17. Right, so we're copying 17 right here. And we're going to go down. And it's right here. I want to redefine the function to be x to the 5th minus x plus 1. So I'm going to come to here, and I'm going to redefine it. Instead of x to the 3rd, I'm going to make it x to the 5th minus x. So I can just remove the 2 times. And instead of plus 2, I'll do plus 1. The rest of it's the same. Okay. So I'm going to execute, make sure it gives me x to the 5th minus x plus 1. All right. Now it tells me I want to start with the seed of 0, set the same accuracy, but change the number of iterations to 30. All right. And call the function. So let's see if I still have it copied. Yeah, I do. Okay. Now, this is called G, so I want to make sure that I set the seed and I told you to set it to be 0. So I set the C to be 0. Accuracy or error is 1 times 10 to the negative 10 power. We're going to change maximum iterations to 30. And make sure that it's calling the function you just defined, which is g and dg dx, all right? If you leave it f, it's going to go up to the last time you defined f and use that function. It'll be the wrong function, right? So make sure that those match, right? And then we're going to execute. Now, this is an interesting one because it actually has a pattern of 3 different values. So first I give it 0, and it finds the tangent line, finds the x-intercept of the tangent line, which was 1. And then it finds the tangent line at 1 on G, and it finds its x-intercept, which is 0.75, right? Then it computes the tangent line at 0.75, finds its x-intercept, which is negative 0.087-ish. And then it finds the tangent line at that value, finds its x-intercept, which is about 1.0033. The next time it does it, it gets 0.750. From there, it goes to negative 0.0825, then to 1.2477, and back to 0.75039. It starts bouncing back to the same values. It's repeating the same 3 values over and over again. So instead of going back and forth between 2 numbers, it's going between 3 numbers and then starting all over again. So it's never going to find the x-intercept, right? So it times out. Now, how do you fix a type 3 error? The same way you fix a type 2 error, which is just choose a slightly different seed, right? So the next thing we want to do, we didn't graph it, which is part of the reason we're having a problem. If we graphed it, we would have gotten better. So we're going to fix the type 3 error now. So the function is still x to the 5th minus x plus 1, which is what you just set it to be in practice 4. So we want to copy the graphing input lines of code. So graphing the function. Okay, so coming up to the last time we graphed was here, right? So I'm going to click in this box, and I'm going to do a Control A, Control C, or Command A, Command C, and I'm going to scroll down. And I figure, put that there. Now you want to make sure that your range values match the domain, which is all reals. So negative 100 to 100 is fine. Negative 1,000 to 1,000 is fine. I don't really know that there aren't some x-intercepts past that, but I mean, you have to start somewhere. Make sure that you use the same name here. So if the last time you defined it as G, which you did, you need to make sure that down here you use G of X, right? And then you want to label G, that's the function, right? So it looks like everything's okay. So let's just execute the graph. And now I can tell that there's 1, all right? And it looks like it's close to 0. If I want to, I can scroll up again to the second graph picture we did up above, where I restricted the X values, and we can Control A, Control C. And then we can come down below that, and we can paste the code. Make sure that it's still using G for the name, all right? And you want to do maybe negative 10 to 5, although I think we could go negative. Well, I don't know, it might not be past, I think it's probably between negative 5 and 5, but I'm not 100%. So I'm just going to execute. I know there is one, so if I graph it and I don't see it, then I've missed it. All right, this one looks like it's close to negative 2. Right? close to -2. So I've got a good seed, -2. So I want to set the seed and call Newton's method. So I'm going to click in this box right here, Control A, Control C, or Command A, Command C. Scroll down, click in the box, paste with Control V or Command V. I want my seed to be the X value here on the X axis of what it looks like it is when it crosses the X axis. So I think it's close to -2. It's not exactly -2, it's less than -2 or more than -2, but that's close enough, right? And did it tell me how many iterations? No, it just said go find it. Okay. So make sure the error is right, the iterations are right. Make sure it's calling it on G, not F, and this is DG, DX, and this is G of solution type, right? So make sure that name matches that name, and that matches what we set for the function. And then we're going to execute. And we got about -1.167. And that's the x-intercept, which looks pretty close. I would have guessed it was maybe a little further to the left, but it looks pretty good. And if I'm not sure, I can always restrict it more. I could even say go from -2 to 0. I mean, oops. I changed the wrong thing. This should be -2 to 2. Let's make this -2 to 2. I changed my y limits and not my x limits by accident, which I noticed because there was no x-intercept. All right, so let's go in closer. Oh yeah, okay. It's right there. So -1.167, whatever it was, right? And that's it. That's the end of the lab. And then to print it, you click on File and Print. So when you click on Print, it will give you something that says Save as PDF. It is possible that it might cut off some of the code. It shouldn't, but it might. If it does, then just take a screen snapshot of the code and put that in there. It looks like when I do this, it saves everything, but I have had a couple of students that for some reason are not getting all of it. Right? And that's it. Do you have any questions?
No, I think it was pretty simple. Just a lot of copying and pasting.
Yeah, just a
Pretty
lot of
much the
copying
answer's
and
just there.
pasting. The main thing is to make sure if you change the name, that you change the name in the command calls.
Right.
That's the biggest problem.
Okay.
But if you copy from the previous example, the name should be right. Okay.
Yeah, had no problems there and got all the same answers. So,
All right. Well, that's it.
all right. Thank you. That
You are
was,
very
was
welcome.
very helpful.
All right. We'll see you tomorrow in class.
Yes.
All right.
Have
Bye-bye.
a good rest of your day.
You too.
Bye-bye.
So I hope this helps you when you're creating your lab and working on your lab. If you have any questions, contact your instructor.